why I want to talk about some of the stuff I'm going to talk about in the next couple of minutes is because, let me start screen sharing so I'm not just completely talking. Okay. So I thought it was kind of cool that in particular the derivation of this coefficient here, alpha, that you use in the lab, it comes from one of the discussion questions down here, the calculation of the B field for a Helmholtz coil, which is your experimental setup for today. It was my homework question 2 weeks ago. So what I'm going to do in this background is give you kind of some of the motivation for a lot of these equations up here. I'm going to show you my homework, and then so I'll just start from the beginning and tell you now that I'm going to show you 1, 2. This one isn't super special. I'll just mention it, and then your job is to do this. So the only discussion question for this week is called final result. I'll put that in the announcement when I post this Zoom recording. So let's start from the top. One of the things, I think actually it might be helpful to look at an experimental apparatus first, because you know, the lab doesn't provide one this week. So in theory, what's going on is that the base of your experiment is applying a voltage across some plates, and it has, similarly to the oscilloscope, it has an electron gun. So electrons are being shot into this kind of glass bulb that you see at the center of your experiment. And what's happening is they're being shot straight initially. However, these coils you see along the outside are both carrying current in the same direction. So the first right-hand rule that you can use in this lab is to curl your fingers. If you see, let me click on this so you can see the arrows of the current a little bit better. Maybe? No, that image doesn't get bigger. So if you look very closely here, you can see that in this depiction, the current is running you know, this way around the thing, and it's similarly in this way. So what we can do is we can curl our fingers. So for instance, you know, if you take your hand and all 4 of your right hand fingers, they curl in the direction of the current, and then your thumb tells you where the magnetic field is. So based on this setup here, with the current going in this way in a loop, our thumb would be pointing this way. So it's pointing, you know, the magnetic field would be an arrow pointing from left to right in this case. And so what does this mean? Let's take a look at this setup. So imagine that, you know, our magnetic field is pointing into the page. So that's what I say when I have this little X, that means it's going into the page, whereas a dot would mean coming out of the page. So this is our kind of electron coming in. It's being shot in from an electron gun. And because the magnetic field is not, you know, being shot into a vacuum, so the charged electron doesn't go straight anymore. And the reason for that is because it's following this Lorentz force law. And this is the second right-hand rule we're going to use. So now, if you can just do this, you know, on the desk or something. If you point your hand in the direction of the velocity, so for instance, our charge, you know, is moving this way. If we point our fingers in this direction, and then we curl our fingers in the direction of B, our thumb, again, now is the direction that the force is felt. So we have velocity, cross B down here, and then our thumb points in the direction of the force. So as we see, this thing is coming in. The force that it initially feels is pushing it, you know, kind of perpendicular. It's always at right angles with cross products like this, because this B is going on the plane, and the B is going into the plane. So we have, you know, kind of a perpendicular situation going on. And so as this continues, it's deflected a little bit, but, you know, the B field is uniform in this area. We'll get to that in a bit as well. It's going in circles. So as this thing comes in, it's deflected a little bit, but the B field is still there when it's here, so it just keeps feeling it. You know, if you have a V here and a B going in, you do the same thing again, and you have a force going this way. So what ends up happening is that the force is continually pushing the particle towards the center. And that's where this centripetal force comes in. If you would like, I could briefly just show you where this centripetal force comes from. I don't remember us covering it in 133, but I'll point you to this book. It's called David Morin's Classical Mechanics book, a very nice classical mechanics book for the undergraduate level. It's kind of geometry focused in this sense, just kind of switching things back and forth to Cartesian and polar coordinates. It's a little bit hard for me to understand. I prefer something that's a little bit more advanced, but actually the steps are much quicker. And down here, we have Newton's law, which says that F equals ma, and this extra term, where this kind of theta dot is the kind of angular velocity. And so that's where this v squared over r comes from, because if you look at the definition of angular velocity, we know that angular velocity, the omega is, that's not what I wanted. It's v over r. Oh, there it was in that little picture right there. Right here. So this is a good Wikipedia article to understand that derivation as well. But if you would like, and you don't want to just take this and run with it, you can ask me, and I can work through the derivation entirely. But anyway, let's just assume that we saw this in 133 and see what happens. The next thing we'll do is similarly to the magnetic force in last lab, because the v is moving in what we'll think of as a plane, and b is moving into the page. Because these things are perpendicular, we know from that a cross b equals sine theta from last week that this can just be written like this, because sine of 90 is just 1. And the thing I'm doing in jumping from this term to this term is just noticing that the particle that's moving is an electron. So E is the charge of the electron. And we'll get to that in a second on the board to talk about what the point of this experiment is. And now we can talk about the next equation that they don't really supply, where this is coming from. Clearly, this is kinetic energy, but they kind of just throw it at you that this is potential energy. So real quickly, I just wanted to explain why that is. We remember from the very beginning of the course where we had this was the force that a charge feels due to another charge. I believe we did this in the conservation of energy lab in 133, that the force is equal to the negative of the derivative of the potential energy. And so if I kind of guess and check, I know that this thing has an r to the second down here. There's really no, I'm just talking about quantities here, so you can just ignore this vector. So what I'm doing is I'm kind of guessing that because this thing is in the denominator, I know I'm going to pick up a minus sign. So the minus sign cancels with this minus sign from the formula over here. And if I take the r derivative of this, I do indeed get the force. And now remember also from lab 1 that we defined the potential, or the electrostatic potential, as kind of everything in the electromagnetic field, the electric field, except the vector. So we have this equation. And so if we look at these two equations, the potential energy and the potential, we see that the only difference is you're multiplying it by the charge. So that's where this comes from. You're replacing this with the electron charge, so EV. And now I just want to talk a bit about, so now we've got all this stuff. You can just find this from rearranging the two equations here. But this is kind of, highly non-trivial. Like I said, it was my homework problem 2 weeks ago, and I struggled with it. So what I wanted to do was kind of explain where things are coming from, what formulas to use, give you, some references. Like for instance, I'll show you, where is it? That one, sorry, I have a million preview pages up at the moment so that I can show you. There's my homework. Try this one. Yes, this one. Not quite though. Here it is. Okay, so what we're going to use this week, you may or may not have seen it so far. I know, you guys may have seen Ampere's law, but there's also something where you can use, if you have a current and you know things about your geometry, you can find out the magnetic field. And so that's what I'm going to work on briefly, and then you're going to do it for the specific case of this experiment. I find the form of this kind of scary, like it's, you're not exactly sure what R is, what this R vector is. It is more or less, you have some reference point R, and this kind of script R value is the difference between the value of the current that you're looking at and the distance that you're measuring. So let me give you an example really quickly. Let's get rid of this thing. I'm looking for cell. And what I'll do is I'll kind of like pause on textbooks that I think, or pages of textbooks that I think are particularly helpful. And then when you guys are, working on the discussion question, you can come back to, pause the video on a particular page. This one and my homework are what I think are more useful. Griffiths is a very popular book for this, but Purcell is a good geometry thing. So this is one route to go about it, but I think the geometry here is a bit better. So let me pull up my homework, which is no. Here it is. Okay. So this is the beginning of my homework where I just worked through one current loop. So one thing to notice about my homework, there's this annoying convention in my grad class that you have to use what's called Gaussian units, whereas we're using something called standard units. The conversion factor is like wherever you see this mu naught thing, for instance, right there in the Biot-Savart law, you replace it with a 4 pi over c. It's just a historical convention. I'm not exactly sure why we need to do it. But anyway, so if you want to convert my answer here, and the only reason I point out my homework is just because it wasn't exactly clear to me in this page of Purcell how we knew what that angle was, like from the geometry. And so I just drew out this figure here that explains it much easier, and gave you kind of the trigonometry and the Pythagorean theorem. So if you were to convert this back to this SI units, you would get exactly what Purcell does here. Where notice that in our case, we're looking at multiple coils. So instead of just I replaced I with Ni, because for each current going around the loop, you have multiple string or multiple coils that are contributing that same current. So I replace I with Ni. And now if you look to the discussion question, it mentions that once you have this result, you don't actually need to do anything new if you have two rings. So it tells us this kind of Helmholtz-like setup. And so you don't need to do anything. You can just talk about the principle of superposition, which if you remember from our standing wave experiment in 133 is that, when two waves meet, they kind of add. So, if you have a wave like this and another wave coming like this, they add up. We'll talk about that in just a second when I talk about the experimental setup. The same thing can be done if you have a magnetic field. So once I have one of them, if, for instance, I had this current loop here and another current loop here, like we do in our experiment, I can just add it on again. So I'm taking all the things out in the front. These are just constants. They don't, they don't have to do with my geometry. So I'm just taking them out in the front, and then I have two setups. And actually, now that I realize my answer is actually wrong, I should have an a over 2 and a negative a over 2. So let me show you the solution of an author, Griffiths, which is, where is it? Here it is. So what you should have, once you identify the fact that in this special circumstance, the kind of special thing about this Helmholtz coil thing is that the distance between your two loops of current is identically equal to the radius of the current. So if you kind of take your hand and look at where you're, on your desk, the current loop is, this big, and the distance between them is the radius. So the reason for that is that the magnetic field in the middle of your current loops is quite constant. And so if you were to look at for instance, the derivative, this third question here, let me go back to my homework. If you were to look at the derivative of this expression in something called Mathematica, or you can just do it online, when you evaluate it at the exact center of the loop, it's 0. So what that says is that the magnetic field is extremely constant. It's a very constant function at the center, and that helps us because it eliminates what you could call noise or something like that when you talk about the magnetic field, because we want the magnetic field to be constant so that our particle experience uniform motion, and we get this kind of centripetal force type thing. And so this is kind of the equation that you would end up with for 2 loops, and the objective of the discussion question is to kind of derive this alpha equation. So this alpha equation arises from the fact that the kind of generic 2-loop Biot-Savart law, if you plug in that the one ring is at half a radius up, one ring is at half a radius down, so the distance between them is the radius, this is the expression you get. So I just, this was kind of a coefficient that they kind of pulled out of thin air, and just the fact that I did this for homework 2 weeks ago, I thought it was a pretty cool expression for you guys to derive to realize why you're using it. So yeah, 1, 2, and 3, you can just take for granted and use either the solution that I showed in Griffiths or my homework solution. And then your job is just to derive the alpha coefficient. So now I'll get on to kind of more practical matters on the chalkboards. I noticed that I don't have, I don't have my floating meeting controls. Oh, okay. Yeah, I hide my floating meeting controls so I can see things, more clearly. And then I can't see that when people have chat or something. So I'll stop recording now, and then after lab, I'll post this and mention again in writing what the discussion question is. But yeah, let me give you some practical tips for the lab, and then we'll get going. Any questions based on that before we get going? Of course, you can feel free to email me if any of that was completely baffling or the centripetal force or anything like that. But if not, I'll stop the recording now.